So that's where I was getting confused.
Mm-hmm. Oh, yeah. No, yeah, you'd have to focus on one carbon at a time.
Like that. Got you. Okay.
And then it works the same way with something with a lone pair. So going back to that water, we got some H's right here, the lone pairs, and we just want to draw a circle around that oxygen. So bisect all the bonds, but include the lone pairs. So it's basically the same as this formula right here, but now we got 6 minus, and we have these two electrons right here, 6 minus 2, 4, and then 5, 6, counting the electrons from the bonds, 6 minus 6, so this oxygen has a formal charge of 0. And that's how I kind of figure it out. I think it's better than doing all that math. Just kind of look at the molecule and see what's surrounding it. But yeah. Oh, didn't mean to do that. All right, so let's move on from formal charge. So let's practice drawing some molecules. So I'm going to do some breakout rooms. If I can figure it out, I'd like to. So we want to do 3 rooms. All right. So I'm gonna break you guys into some breakout rooms. I think when you guys go into the breakout rooms, you won't be able to see my PowerPoint anymore. So I'll go ahead and join and let you guys know which one to do. Yeah. Oh, let's see. I can see it right here. So in breakout room 1, breakout room 1 consists of Pablo, Melissa, Angie, and Alejandro. So you guys are gonna do the first one. So HNO3. I'd like for you guys to draw that. The second one consists of Dilene, Lex, which I'm guessing is Alexis, Masha, and Sophia. So you guys will do a HClO, LO3. So you guys do chloric acid. And then breakout room 3 will consist of Che, Leslie, and myself to kind of even it out. So us 3 will be in charge of H2SO4. So any questions? Everyone know what they're going to do?
Yes.
Alrighty, cool. So let us go. Someone can join their respective breakout rooms. Alrighty, you all. Are you ready to do some drawing?
To do some what?
Do some drawing?
Some drawings, yeah.
So we are in charge of H2SO4. Let me draw with this right here.
Okay, so we could start off by saying we know H has 1, and it's 2 H's, so that'll be 2. And then SO4, how many valence electrons does it have?
6.
6, yeah, because it's in group 6A.
Yeah.
So we should have a total of 8, right?
1, 2, 3, 4, 5, 6. And then you have to multiply it by the 4 on the oxygen. So its oxygen is, right?
Mm-hmm.
So that'll be 24 plus 2. So it's a total of 26 valence electrons.
And then you
Yeah.
start off by drawing the S in the middle.
Okay, so we got I guess I'll do the drawing. You guys just tell me what to do.
Okay. So S in the middle.
It's in the middle.
Then 4 surrounding oxygens.
Okay, got some oxygens.
And then 2 of those oxygens would be double bonds. And then 2 would be just 1 bond.
Okay.
And then the ones with the 1 bond, they have the hydrogen attached to them.
Dang, Leslie, good at this.
Sorry, it's because I have
Taking
Dr.
charge.
Novodone and he gave us like a little cheat sheet on how to do them.
What the hell, yo? I should.
I have to share it with you. I have to share it with you, Trey.
Please do. Please do. I'm begging you. Please.
Let me
because
text
I'm
you it.
struggling with this.
Wait.
So is this it?
And Leslie, we both live on the west side, so you can meet up with me and help me out.
No, I don't live in the west. I live in the east side. I told you.
Shit. Damn it. Well, I'm willing to drive to the east side. Just let me know.
I do actually need to. We need to get together. But I just honestly like. I know we texted and we talked about meeting, but I've been so busy. I have 17 hours this semester.
Me too. So I totally understand because I'm pre-med, so I know how much work you have to do. So I totally get it.
All right. So is this it, everyone? Is this the answer?
Yeah, I believe so.
Oh no, there's on each double bonded oxygen there's 4 lone. I don't know how to say that. 4 lone electrons. So
Some lone pairs.
yeah, and then the other O's have another 2.
Mm-hmm. So just like this.
Yes, sir.
Alrighty. Yeah. So yeah, that's good.
2, 4, and then
That's
6.
good for me.
2, 4.
So the way that I like to remember when it comes to oxygens are always going to show up as like this, double bonded with that with those 2 like that,
Mm-hmm.
or they're going to show up like this. And these 2 are the only way that oxygen wants to show up. Sometimes you see it showing up like this, but this is when the oxygen has a formal charge of -1. But yeah, these is like what oxygen wants to shoot for. Does that make sense? So most oxygens are going to look like that.
Okay. I'm writing this down.
Write it down. All right. So I'm going to go check on the other groups.
Okay.
So yeah.
Yeah, Leslie, if you have the cheat sheet or whatever, just totally send it to me, man. Let me look at it because I have 3 labs, 4 classes, and 2 workshops.
Hello, everyone. How's the drawing going?
I think I got it. I'm not sure.
Think you got it? All right. You can go ahead and draw it on the whiteboard if you want. I think you got to go to like annotate or something.
Let me
I should say like some
see.
options.
Annotate. Oh, yeah. Oh my god. Man, this is hard. Got the N in the middle. And
Mm.
then oxygen. It's hard.
Okay. Okay.
And I put just an H with the hydrogen. And then I did that. And then there's double one, but I'm not sure.
Mm-hmm.
And here I did. Oh. And then I did like, but I'm not sure. Like that's how I have it.
Yeah, that looks pretty good. Pretty close. I think the only part you may have messed up on was those last two lone pairs.
Oh,
But yeah, that looks good. Let me move myself to this one. So yeah, that looks pretty good. Definitely got the right idea. So let me put my drawing. So you were right. N double bond to the O with the 2. And that one's got the 3. And then you got that OH group.
mhm.
And yeah, that oxygen does need another 2 to be happy. So we kind of draw it something like this.
Oh, okay.
Yeah. But yeah, I get like your mindset and like what they were doing. So yeah, that makes sense. So yeah, good job. Hello, everyone.
Hi.
Hello.
You guys have the answer. You ready to present?
Yeah.
You guys got it?
Yes.
Alrighty. Where is my Zoom thing? So I guess you guys won't have a problem drawing it for everyone?
No.
Alrighty, cool. I like the confidence. So let's all go back to the main room. Alrighty. So, the people from breakout room 2 offered to draw for everybody. Draw some pretty pictures. So let's go ahead and do that. So there you guys go. If you're from breakout room 2,
Yes.
you should be able to
Yes.
draw on the screen.
Okay. This is the other, okay?
Mm-hmm.
After the exam is on, and we could help each other out.
Yeah, for sure.
Hello, everyone.
Hello.
I
lost.
Yeah, I'm not too sure what happened.
Okay. Okay.
Let me put the whiteboard back up.
Okay. Thank you.
Okay.
Okay. Okay. Another line.
Mm-hmm.
This is the other, okay? Sorry for what I think.
Oh no, you're good.
Okay.
All right. So let me kind of
Okay.
all right. What does everyone think? Does this look like forecasted? She has something like this.
Yes. Yes.
All right. What do you all think? Is she right? Is she wrong?
It looks good.
Looks good?
I will make an educated guess and say it looks good.
Nice. I concur. Looks good to me. So does anybody have any questions on drawing some stuff? It could be a little daunting, but I recommend just practice. Practice is like the number one thing. So yeah, that being said, let us go ahead and go back to the PowerPoint. So we drew the following. The next thing we're going to cover is electronegativity. So can someone tell me what electronegativity is? Kind of in their own words. Do you guys remember from Chem 1?
Isn't it that like like how, well, obviously there's a trend on the periodic table, but it's just how negative an electron is, how positive it wants to be. Something
Kind
like
of,
that.
yeah. Yeah, I kind of see what you're saying.
Marco, is it kind of like how the atom, like how it attracts like a certain level of like negative charge, like electrons? So it's like how the atom is like pulling in a negative charge electron, right? Okay.
Yeah, that's spot on. So as you can see on the PowerPoint, I written electronegativity is the tendency of an atom to want to pull electrons towards itself. So it wants to take in electrons so that way it could reach noble gas configuration. On the left, you see fluorine. So you kind of see it's missing one more electron. So that one really wants to have another electron. That being compared to like group 1 elements, so something like sodium, potassium, those have noble gas configuration +1. So they really want to get rid of an electron. So that way they could reach the noble gas configuration. Some stuff to note: fluorine is the most electronegative atom. And if we jump to the next slide, actually, right here is how electronegativity increases. So as you move to the right of the periodic table, you get increasing electronegativity number things. And as you go up, so as you can see, fluorine is the most electronegative atom. And we can kind of go back and look at that other one. And shielding, I think it's atomic shielding or something like that, tells us why larger atoms are less electronegative than smaller ones. So you can kind of think of it as the iodine. What happens if I do this? Oh, I don't want to do that. So the iodine on the right has all those electrons. And while iodine is in like the halogens and it's all the way to the right, it is less electronegative because for it to attract another electron, it kind of has to, that positive charge kind of has to work through all those electrons. Whereas on the F, the nucleus, the positively charged center, is more exposed to the electrons it wants to take in. And yeah, does that kind of make sense to everyone?
Yes.
Yeah, all right, cool. So again, here's the periodic table with the arrows. So resonance. Resonance is how we explain basically a depiction of how electrons can move through a molecule when there's a difference in formal charge. So this molecule right here, O3, ozone, this is how we draw it on the left. However, it can also go and shift to the right. So for instance, this bond right here can move over here. And basically it's doing this multiple times a second. So another way we could kind of draw it is each like this and then kind of like a dotted line to represent that there is a double bond, but it's kind of moving between those two positions within the molecule. And on the bottom there, you can see NO3 minus, so nitrate. Because of the way it's drawn, it can be drawn 3 different ways. So one with a double bond on top, one going to the left, and one going to the right. And all of those are accurate representations of nitrates, and they're all kind of switching back and forth as time progresses, basically.
So question, Marco. So if a question like this comes up on the exam and they have different ways of showing it, then all of them are correct, right? Because not just one.
Mm-hmm.
Okay.
Yes.
You said we have to draw all of them.
Yeah. If it's asking you to draw the resonance, then all of them will have to be included.
Yeah, so heads up.
Yeah. Heads up. So, are there any more questions on the resonance?
So when you have a double bond on, so only time the resonance really only time you have like multiple is like a problem like this. Say if you have a double bond and a single bond on one side and there's different ways of structuring it, then that's when you have more than one. But if we had a double bond on each side, then it would only be one, correct?
Mm-hmm.
Okay.
Yeah, so for instance, this molecule right here, carbon dioxide, this one would only have one resonance structure because you can't really move anything around.
Got you.
So yeah. All right. So the next thing we're going to cover is hybridization. So hybridization is something we use to explain how orbitals look when atoms bond to each other. Kinda. It's kind of a little bit more complex. But for this course, basically you want to focus on identifying the hybridization of specific atoms. So in this case, we have water, some H2O. And the first thing we're going to do so we're going to look at the oxygen in this case and see how it's hybridized. And the first thing we want to do is look at how many electron densities are around an atom. So in this case, we have 1 electron density, 2, 3, and 4. So the bonds count as electron densities, and so do each lone pair. They both count individually. So once we do that, we just count in order of hybridization. So the first hybridization kind of thing is S. It goes to SP, SP2, SP3, SP3D, and SP3D2, and it goes on. But in this case, because we have 4 electron densities, what is our hybridization?
Is it SP3?
Mm-hmm. SP3. That is right. So yeah. Any questions on hybridization? I believe it was covered in Chem 1. So hopefully you guys are kind of familiar with it.
This lecture is being recorded, right?
Yeah, I started kind of late, but yeah, it's being recorded.
All right.
So yeah, I believe you have a similar chart in your workbook. I don't know off the top of my head, but yeah.
The last, like the back cover.
Oh yes, yeah, it's on the back cover. So on your periodic table, if you just flip it to the other side, it tells you your hybridization chart thing. All right. So let's do some hybridization practices. Let me call on some people. So Pablo, what do you think our hybridization is for that methane?
For methane?
Mm-hmm.
I think 4.
Oh, what? I don't think I
What was
heard
it?
you. 4?
Yeah.
Yeah, so we have 4 electron densities. So going back to this chart, if we have 4 electron densities, what is our hybridization?
SP3.
SP3. Mm-hmm. You kind of
I have a question.
go ahead.
Is I guess the density, is it for each bond that's made?
Yeah, each bond counts as a electron density. So we could kind of just count it out. We know it's a S, SP, SP2, SP3. And that's how I figure it out.
Okay.
So using that same logic, Dilene, what do you think about that next one? SF6. Kind of scary looking.
Sorry, I'm not used to listen my name like that. It's like
Oh,
in
I'm sorry.
Spanish.
How do you pronounce it?
Dilean, like in Spanish.
Oh, okay, yeah.
Yeah.
Dilene.
It's
Sorry.
SP3D2.
SP3D2. Mm-hmm. That sounds about right. So let's go ahead and count them. So we got S, SP, SP2, SP3, SP3D, SP3D2. So yeah, good job, Dilian. Sorry if I played
Thank
it
you.
wrong.
Nice try.
Okay, I'm sorry. So let's see. Alexandra, what do you think about that last one?
So I'm not sure if the electrons in the center, I don't make any difference, but I would go with sp2.
Close. So those lone pairs do count as a electron density. They both count for 1.
Okay, so sp3 then.
So S, SP, SP2, and SP3. So yeah, SP3. Good job. So any questions on the hybridization? You kind of just have to memorize kind of the right side of this chart. Learn how to count throughout them, like S, SP, SP2, SP3. And I think when you kind of figure that out, it kind of comes a little easier. But yeah. So any questions on hybridization? It can be a little daunting. All right, I'm guessing no questions. Yeah. So let's move on to the VSEPR theory. So this is kind of a theory on how we imagine molecules to look in space, and where other atoms are in relation to that central atom. So in this case, our central atom would be this carbon right here. This is methane, so CH4. And yeah, using the Vesper theory, if you look at that same chart in the back of your workbook, it could kind of help you identify what shape a molecule is. On the left, I have the ball and stick representation of methane. And on the right, I kind of drew, or I didn't draw it, but I included a picture of a tetrahedron. So that's kind of the shape that it's resembling. So we call that molecule tetrahedral shaped. And we could look at that on the back of our workbook. So we see we have 4 bonds. So electron regions around the central atom, we would go to 4, and we have 0 lone pairs. So if we follow that chart, we can see that the electronic and the molecular geometry are all tetrahedral. Something you guys don't have to do, but I kind of, I recommend it. It kind of helps out a little bit, is to buy like a little molecule kit thing, so you can make something like this. So this is what we have on the screen, but being able to hold it in your hand, I think it helps out a lot. But completely unnecessary if you don't really want to buy it. I think it helped me out a lot to kind of visualize what's going on, because the Vesper theory can be a little hard to comprehend when you think about something so small. So having something in your hand kind of helps out. But yeah, so we got a little animation to kind of just solidify the fact that we're just naming what the molecule kind of looks like. And something also included here on the slide is that atoms always want to be as far away from each other as possible, and that electrons need more breathing room and require more space. So as you can see, those 4 hydrogens are as far away as they could get from each other surrounding that central carbon. And if we were to have electrons, they would kind of occupy more space. And let's say, for instance, this top one was like lone pair electrons. All of these 3 would be kind of pushed down a little bit because of the influence of those lone pairs. And yeah. Any questions on the VSEPR theory? Hopefully you guys have been hearing all these concepts in lecture. But yeah. If there are no questions, I believe I have some practice problems. All right. So let's see. I'm gonna go ahead and call in some more people. Alrighty. So Masha, what would you say our electronic geometry is for that first one, water?
Can you ask another time?
I'm
Please
sorry.
say another time.
Oh, that what do you think our electronic geometry is for water? That first one, H2O.
Electronic geometry?
Mm-hmm. Which shape is water?
think something like a triangle.
Yeah, kind of. That's how it appears on like the two-dimensional Lewis structure. Do you have the workbook by chance?
No.
No. All right. Let me see if I can find a picture of the thing. All right. So this is kind of what the chart looks like for anybody who doesn't have the workbook yet. So using this chart, what would you say our H2O looks like? So we see on the right here total domains. That kind of means how many electron densities there are surrounding it. So if we were to look back at water, what would you say, how many electron domains do we have? Anybody could shout out the answer. What is our magic number? How many
Three.
electron densities do we have?
3.
3.
Yeah.
Close. So remember, each
Four.
lone pair counts as 1.
Oh, okay. I'm sorry.
Mhm.
I tried.
Yeah, no, I'm trying. So I heard someone say 4. Do you all agree that there's 4?
Yes.
Yes.
Yeah. So we got 1, 2, 3, 4. So there are 4 electron densities, and in your workbook, I believe it shows up as the magic number. So we know we have 4. So we're gonna be looking at this section right here.
So tetrahedral.
So how many lone pairs do we have?
Two.
2 lone pairs. So we could look at this section right here because it tells us 2 lone pairs. So using this information, what is our electronic geometry? Electron geometry.
Bent. Oh no, tetrahedral. Sorry.
Tetrahedral. Yeah. So our electronic geometry is tetrahedral. But our molecular shape, what is that? You kind of said it right now.
Bent.
So our molecular shape is bent. And yeah, that is kind of the VSEPR theory. Let's go back. Where are we? All right. So who wants to try this one right here? Our carbon dioxide.
I'll try that one out. Let me see if I can do it.
All right.
So, I guess I'll start off with the number of electron densities. So it has 1, 2, 3, 4. 1, 2, 3, 4.
So remember,
Yes, 1, 2, 3, 4, right?
close. I kind of see how you would think it's 4, but remember, double bond. Kind of think of it occupying the same space. So like, we would draw it like this. That would be like an electron density.
So then that means it's actually 6, right? 6 of them?
Well, we're only thinking about the carbon in the middle. We're thinking about our central atom. How many electron densities are coming out of our central atom?
Two.
2. So we got one right here, one right here. So we have 2 electron densities. How many lone pairs do we have
4.
on the central atom?
No, on the central atom, no. You don't have any.
All right. So let's look at that chart. If we have 2 domains and 0 lone pairs, what is our shape?
It will be linear.
Linear. And that would be for both our molecular shape and our electronic geometry. So linear, linear, and yeah. Good job. So yeah, just keep in mind that when we're trying to figure out the shape of the molecules, we really want to focus on the central atom. So any lone pairs or any bonds coming off of the atoms attached, we want to pay attention to the central atom.
Okay.
So what about SF6? Anyone want to give that a crack? How many electron densities do we have?
6.
6. Yeah, so we got this right here. Oh. We have 1, 2, 3, 4, 5, and 6. So how many lone pairs do we have?
0.
0. So if we have 6 electron densities and 0 lone pairs, what would be our electronic geometry?
Octahedral.
Octahedral. That would be correct. So 6, 0, octahedral. All right, so let's do that next one. So NH3, what do you guys think?
So you have 4 electron densities.
4.
And you have
1 lone pair.
1 lone pair.
All right, so we're kind of mixing it up. What do you guys think?
So that would be tetrahedral.
That would be our electronic geometry, would be tetrahedral. What about the molecular shape? What do you guys think about that?
It will be a triangular pyramid. Well, how do you say it?
Yeah, trigonal pyramidal.
Yeah.
So a pyramid in the shape of a triangle. And yeah. And let's do that last one. OF3. F3O. What do you guys think?
It has 3 EDs, I think.
3 electron densities. How many lone pairs?
0.
0 lone pairs. So what do we call that?
Trigonal planar, I think.
So trigonal planar would be this molecule right here. And yeah, that is all of the practice ones. Any questions on this Vesper theory? Like I said with the Lewis structures, really you just want to go through the workbook and practice as many problems as you can, and it'll become a little bit easier in time.
Well, you explained it a lot better than Professor did, so thank you, because I understand it.
Yeah.
Yeah, thank you guys. I'm just here trying to explain it in, young people talk. No, I'm just kidding. But yeah, like I said, highly recommend these little molecular model kits. I think they really do help out a lot. But
Where exactly do they sell them at? You tell us where to buy it?
I just got it on Amazon. It was like maybe $12. I don't know where they sell it retail. But yeah, just Amazon. Kind of helps to visualize all these. Like if you were to just read trigonal bipyramidal, you'd be like, what does that even mean? But it kind of helps to have it in your hand. So yeah, here's that chart again. So any questions on anything that we've covered? I think we're reaching about the end of my PowerPoint. No questions. Alrighty. So if there are no more questions, I do have a quiz, unfortunately. So, just like before, you guys need to choose a representative to give you the final answers for the class and to be the sole answer for the last question. So I believe last time your representative was Pablo was the representative.
Yeah, it was me last time.
Who's it going to be this time? How
Do
about
we each
Angie?
answer?
Oh, that what? Chet, sorry.
No, I was asking if we could each answer one, so we don't put all of this on somebody's back.
Oh no, yeah. For these first couple ones, you guys can answer as a class. It's like kind of a class quiz. So Angie, I would like for you to be giving me the answers that your classmates decide upon. All right. So question number 1, what is the hybridization of carbon in methane, CH4?
It is a 4 sp3.
sp2?
sp3
Let's see.
4.
Yeah.
You guys discuss amongst
sp3.
yourselves. I'll give you a hand and draw it out for you. What do you think, Angie? What are your classmates saying?
Yeah. sp3.
sp3. Final answer?
Yeah.
That is correct. Good job. All right. Number 2, sulfate. How many resonance structures are there? This was kind of a tough one. I'll give you guys a minute to think about that one. Yeah. Let's see. Let's see what you guys are saying.
Yeah, I think 6.
You think 6?
Yeah, 6. 6.
See. I think the overwhelming majority of people are saying 6. That would be correct. Good job. So let's think about it. So sulfate we know is something like this. S O O O O. And we could have a double bond here and here. And then we could have here, here. Double bond here, here. Here. And then kind of right here. And then right here. And that would be 6 different resonance structures. They would all be correct. So yeah, there would be 6. Alrighty, what about this next one? This one looks kind of like a doozy. Place the following in order based on increasing electronegativity. So I want the most electronegative on the right and the least on the left. So yeah, go ahead. Looks like fun. Let's see.
Yeah, I think it's potassium, and then calcium, lithium, oxygen, and fluoride. I'm not sure though about lithium and calcium.
Not sure about lithium and calcium. What do you guys think?
Like,
Is what she told me correct? Alexis thinks it's a little different.
mhm.
Why do you think it's a little different than that?
Before calcium.
Lithium before calcium.
Yeah.
And why would it be before calcium?
Because lithium is in the first family.
Lithium is in the first family. But does that mean it's more electronegative? What do you guys think?
No, isn't it the trend? Go from like top to left. I mean top to right. So calcium hits before lithium.
Sounds good to me. What about you, Angie? Is that the final answer?
Sure.
All right. So yeah, that is correct. It would be potassium, calcium, and then lithium, oxygen, fluorine. So let's go back to this one right here. So where's my pen? We have, whenever we're ranking in terms of electronegativity, we want to look at whatever is basically in the bottom left. Everything in the bottom left we know is going to be weaker than basically what's up here. So the trend, like she was saying, goes this way. So think of it like that. So anything closer to that bottom left would be weaker. So in this case, K is our closest, and then Ca is next. And then because it becomes increasing with strength, the higher you go, lithium would have a higher electronegativity. And then we just move to the right, OF. So yeah, good job on that one.
So it's potassium, calcium, lithium, oxygen, and then fluorine, right?
I
Mhm.
just searched for the electronegativities of both, and the lithium is less electronegativity than calcium. It's like by a little thing, but it's less than calcium, actually.
Really?
Yep.
Oh man. Let me see.
And I think in the Shang, it's a periodic table with the electronegativity. Let me-
Because what I thought it was potassium, lithium, calcium, oxygen, and then fluorine. That's what I thought it was.
Well, then why do we would have trends then? Like, why would they always say that?
Yeah, I don't know.
Huh.
Who knows?
It looks like that is about right, yeah. So yeah, I guess it would be like that. I'll have to check up on this and then get back to you guys. But yeah, it looks like calcium and lithium are pretty neck and neck when in terms of electronegativity.
So do we ever even follow the trend now, or?
No, the trend definitely is there. For instance, cesium, that bottom left, the electronegativity of that is 0.7 compared to fluorine, which is 4.0. So the trend definitely still holds. And I would go by the trend if I were you guys on like the exams. But
Okay.
yeah, that is interesting. I'll have to check up on this and I'll get back to you guys. So I guess that seems kind of like a broken question that I asked. So I'll just give you the point for that one. The final answer would be potassium, lithium, calcium, and then OF would be the final answer, I suppose, based on like the hard numbers. Yeah. I don't know. I
Could
see.
you repeat it one more time? Oh, I'm so sorry.
Oh no, you're good.
So potassium, lithium, calcium, oxygen, fluorine.
Potassium, calcium, lithium, oxygen, fluorine. Let me just double check that. Electronegativity. Let's see. So the electronegativity for lithium is, let me see, 0.98. Then calcium shows up as 1. I don't know. I'll get back to you guys on this one.
Okay.
But yeah, definitely hold true to the trends. That's what they taught me, and that's what probably you'll be tested on. But I will report back. All right. So let's move on to number 4. What is the formal charge of nitrogen in NH4 plus ammonium? What do you guys think? I'll do you a favor and draw it for you. So that is ammonium. What is the formal charge of nitrogen?
It'll be 4, right?
Would it?
Hold on, no. Never mind. I'll take that.
I got 1.
1, yeah.
1.
It's 5 minus 1.
Minus 1? Plus 1?
Oh, 5.
It is a
Yeah,
plus 1 because nitrogen
5
is
minus
group
1
5.
equals 1.
So I heard, I believe that was Masha say it. Masha, can you repeat what you just said?
Nitrogen is group 5, and I think it's plus 1.
Then you think the answer is plus 1?
Yes.
So something like this. What do you guys think? Do you all agree?
Yeah, I think I got plus 1 too.
I got 1.
All right. So that would be correct. The answer would be plus 1. So we look at the valence electrons for nitrogen. How many valence electrons does nitrogen have?
5.
5. So if we do my little circle thing, how many electrons are surrounding the nitrogen? 4.
4.
Yeah. So we do 5 minus 4, and we get positive 1 as our answer.
Okay.
All right. What about this next one? What is the geometry of this molecule? And we want to focus on C being our central atom.
Okay, so would you have 3 electron densities, and then you will have, how many lone pairs? You have 1, 2, 3, 4.
Is it no
Lone?
lone pairs, I think?
Yeah, no lone pairs.
Yeah, a trigonal planar.
Trigonal planar.
Mm-hmm.
Everyone agree? Trigonal planar?
Yes.
Are you sure? You don't want to change your answer?
No.
You are correct. It would be trigonal planar. So, how many electron densities do we have?
3.
So we got this one, and this one. How many lone pairs?
0.
0 lone pairs. And then using that information, we just refer back to our chart. Trigonal planar. That is correct. All right.
Marco, can you do me a favor? Could you go over number 2 one more time for me? Because I got that one wrong. So, because I was doing it on my own.
Okay, yeah. So let's see, number 2. How many resin structures are there for sulfate? So we could draw sulfate, and then we just go ahead. Yeah, Masha, you can go ahead. The rest will be recorded, so you could just always refer back.
Thank you. Goodbye.
Goodbye. So sulfate looks something like this. And I believe it's like this. So this is our sulfate ion. So using this as our starting point, we could change where the double bond is. So we could draw different resonance structures. So for instance, we could have the double bond looking something like, it could go like this, and then have our 2 single bonds like that. I'm not gonna try the whole molecule over and over again. I'll just do like the S thing. And similarly, if we could go to the right, we could also move it to the left, have it look like that. We could have it go completely sideways, and then we could do the corner but to the bottom. And then using all these different resonance structures, we could just count them up and see that there are 6 different kinds of ways we could draw sulfates.
Gotcha. Okay. I got it now. Thank you. I
Mhm.
appreciate that.
Yeah, no problem. Any questions on these first 5 questions of the quiz? I think I got 2 more. There's 3 more. I don't know. All right. So let's see. How many grams of H are in 500 moles of CH2O? Formaldehyde. A little throwback to module 1.
Yes.
Grams of H. You know, I'm gonna stop sharing my screen for a quick minute.
What? How many? What was the question again?
How many grams of H? Here,
Oh,
let me
grams.
up again.
Okay. Thank you. No, that's fine. Thank you.
Okay. I'm sorry. There we go.
No, it's all good. Sorry, I wrote everything down except
Oh,
that.
no, yeah. It's all right. I was just making a quick little edit to my PowerPoint, but now it is good. Delianne thinks it's 1,000 grams. And correct me if I'm saying your name wrong.
It's okay.
Delianne? Sophia says 1,008. IDK about the sig figs. Good question. What about the sig figs? Let's see. I want to hear from a couple more of you before I take a final answer. Angie says 1,008. What do you all think? Is Angie right? She speaks for you guys. She's like the Lorax, but for chemistry. Because he speaks for the trees. I don't know if you got it. That's getting fancy. 1 times 10 to the 3rd grams of H. That's true. What about the units? Numbers including units. 1.00. So, yeah. Angie, what do you think? Final answer. You're going with 1,000?
Yeah, I think I'm going with 1,008 grams of
1,008. Mm-hmm. Yeah. So it would be 1,008. So 1,000 is also correct. Because I know some basically, yeah, let me just draw it out for you guys. So let's go ahead and do the math. So we have 500 moles of our CH2O. And we know that for every 1 mole of that, we get 1 mole of H. No, 2 moles. So, and we know that every mole of hydrogen weighs 1 gram. And if you look at your periodic table, it tells you that it weighs 1.008 grams. So really, I would accept both answers. They're kind of the same. 1 gram of H. So we just multiply across 500 times 2, 1,000. So it'd be 1.00, 10 to the 3rd grams H. And that's how we would come up with that answer. So yeah. What about that next problem? Name ClO minus. Gotta think back. Gotta remember.
Would that be hypo
I
chloride?
think it's hypochlorite.
Hypochlorite, yeah.
Yeah, hypochlorite.
Hypochlorite. Looks like the majority of you are saying hypochlorite. And yeah, that would be correct. So what is a reference number for chlorine?
3?
3.
Sorry.
Yeah, so it's 3. So we see we're missing 2 oxygens. So yeah, you guys are correct. It would be hypochlorite. Alrighty. So this one you guys can still help each other out, but I would like for someone, whoever's the best drawer, to draw nitric acid. You guys can give each other hints, help each other out, give each other information. But try drawing nitric acid. Someone put the formula. Nice. HNO3. Excuse me.
5, 6 es 18.
And we'll go in the middle. Oxygen.
Dang.
How do you use the whiteboard again?
I think if you go to like the top of the screen or the bottom, it gives you like the more option or annotate. Basically, you just want to annotate. I think everyone should have permission to annotate.
Okay, then.
My Google is listening to me. Are you guys having trouble with the drawing? Or are you still trying to come up with it?
Mm,
Who's gonna draw it?
Someone's got to draw it.
Hmm.
I want
How
someone
can
to draw.
Well, I'll draw it. Let me see.
I can draw, but I don't know how to do it here.
Okay. So ugly. Oops. Oh my. That I think.
What do you guys think? Do you agree? Alejandro agrees.
do we have to put the charges like on the atoms that are charged?
Hey, babe.
No. You don't have to
Class.
keep formal charge.
Oh, okay. Just call to tell you have a good day. I love you.
Oh, I love you too. Have fun.
I bet.
Oh, okay.
How sweet.
What's Junie doing in class too?
Yeah, in class.
Okay. You guys work hard.
Okay, we will.
All right, man. I love you.
Love you too. Bye.
Alrighty.
I wasn't on mute. I'm so sorry.
Oh no.
I thought I was muted. I'm sorry. My husband's hunting, so he's out of town, so he was calling me.
No.
I'm sorry.
I I don't want to get in the way of love, you know.
Embarrassing. I'm sorry.
Okay. Cool. Nice. So yeah, nitric acid. Everyone agree?
Yes.
Mm-hmm. So it sounds like the majority of you guys agree. I also agree. That looks good to me. Alrighty. Now for the last question. This one is for, who's it, Angie? Angie, is for you only. You're not allowed to get any help. Are you ready?
Yeah.
Alrighty. There you go. Let's go from 1 to 10. 100. 0 to 100. How funny was my joke?
1,000.
Dang. That is a good answer. I will accept it.
I
All
get
right.
extra points. I'm kidding.
All right. So you guys
There.
passed the quiz. Flying colors. So yeah. I don't know why it's not clearing. Any
Wow.
questions on anything that we covered today?
Nope.
No? Alrighty. I hope you guys did some good learning today. Yeah, just practice, practice, practice. But that's all I have planned for today. So if there are no questions, you guys are free to go. Go about your lives.
All right. So, Marco, I hope you don't mind me saying this, but Alexis and anyone else that's interested in meeting up at the library or something, my number is there. So if you guys create, you guys post your number as well, and someone create like a group text, we could meet up and help each other out. If you guys are down to do that, just let me know. I live like 8 minutes from school, so just let me know. All right, Marco, you have a good one.
Yeah, you too. Take care. Thank you guys.
See you.
Adios.
I have a question.
Go ahead.
Sorry, I was distracted by that phone call. But so it was nitric acid, right?
Mm-hmm.
So it'd be nitric, it'd be NO2.
So what was the mnemonic? I asked you guys to remember.
I remember it as ic-8-itis.
Oh, that's cool.
I don't know
So
the itis means.
it corresponds to 8. So what does 8
Yeah.
indicate?
So A is just the regular amount. So NO3 -1, right?
Mm-hmm.
Okay. So, but doesn't it? Okay, so I drew it as how many? 1, 2, 3, 4, 5. Yeah. So I drew it N with 2 double bonds and 1 oxygen bond. Do you want me to draw it?
If you can, yeah. Let me.
Yeah, I think I
I don't know
can.
why it's not erasing. Oh, that's because I didn't draw that.
Okay, I can draw it on the side.
Okay.
So I got so it's NO3, and then since it's an acid, it has an H.
Mm-hmm.
So I did sorry, that's crappy. And then I drew that. Wait, am I getting something wrong? Like, what am I doing? Oh, and then the H, sorry, hold on. The H is actually, oh, oops.
Uh-huh.
Yeah.
Uh,
If that makes any sense.
yeah, no, I understand that. Let me take care of this group chat thing real quick, and then I will answer your question.
Okay.
So those of you who are not in the group chat, where's my phone? I can add you if you post your phone number. I should be able to add you. I think some of you already did, maybe. So I go ahead and add you guys real quick. Cam members, add members. 5. This is Alexandra. And let's see. And then for the numbers from Mexico, I don't think I could add you. I don't think it works. Let me try that real quick. So we got 6. Nine. 2, 2. Yeah, I don't think it's gonna let me add you. I'll try to come up with a way. I'll talk to the other peer leaders and see what they're doing about that. But just keep an eye out for Blackboard announcements. And if you have any questions, feel free to email me. And I put my cell phone number on the syllabus. So if you have any questions, just shoot me a text if I don't answer your email timely. But yeah. So let's see. Let's look at this nitric acid problem. So you are correct in like the oxygens. I see how you want to, I think you need to add plus 52, then the number. Let me try that. Plus.
Would it be better to draw out like the nitrate first and then add the H? Because that's what I think that's what I did.
Mm-hmm. Yeah, so the only issue with what you've drawn right now is look at how many electrons are attached to the nitrogen. And does that break the octet rule?
1, 2, 3. Oh, well, there's only 5 showing. So do I need?
Mm-hmm.
Okay.
Well, so remember each lone pair, each bond counts as 2.
Oh,
So
okay.
how many electrons are attached to that nitrogen?
Oh, okay. Yeah, there's 10. Yeah.
Okay, let's see. So that plus 52 thing worked. Let's see, plus 52. And then this is Angie. Okay, cool. It looks like I added you guys. I think that's everyone. Yeah. So yeah, let's draw this nitric acid out. So we could start off with what you've drawn here. So one way that we could remedy this, because the nitrogen has 2, 4, 6, 8, 10, basically what we could do is just get rid of one of the double bonds and move it over to the oxygen.
Okay.
So it would turn into an oxygen on this side with the 3. And unfortunately, it looks like we're gonna have to do the oxygen like this. So it's gonna have a formal charge of -1 because it has 7 electrons surrounding it.
Okay.
And then the nitrogen is gonna have the 8. So now the nitrogen is satisfied. The oxygen is, all the oxygens are satisfied. And our nitrogen has a formal charge of +1. So those formal charges will cancel each other out.
Oh, okay.
That's
Yeah,
how
I get it. I didn't do that one.
Mm-hmm.
Thank you.
Yeah, no problem.
And sorry about that phone call.
Oh no, it was beautiful. You know, love is in the air. All right, cool. Let's see. I'm going to go ahead and stop recording now.